Hello, everyone, and welcome back. This is Mr. Cobalt. I'm Mr. Cobalt. This video is going to be going over titration and of a weak acid with a strong base. I'm continuing on from the second part, and this will be the last part. So I only have a little bit more to go. We just finished up calculating the pH of the solution after adding 30 milliliters of your NaOH, and we realize that that is a strong base problem. So we have leftover at that point. We have leftover OH minus hydroxide ion, and so that's going to be the major overwhelming contributing factor to the pH. And so at this point, from this point on, any strong base that's added to your problem is going to be a base that's going to be influencing the pH. So only the amount of base you're adding is going to influence the pH from this point on. And so at the last part here, calculating the pH after adding 35, 40, and 50 milliliters, the way you calculate that is exactly the way you calculated with 30 milliliters. The only difference is that you're going to end up with more of your OH minus left over. So if you add 35 milliliters, then you're going to end up with a little bit more of your OH minus, and then so you're going to then calculate the concentration of that OH minus, and then from the concentration of OH minus, find the concentration of H plus, and then plug that into your negative log and get the pH. So so I already did that for you. So for these three, we have for 35 milliliters, it's 12.22. So 12.22 for 35 milliliters. For 40, it's 1236. 1236, and for 50 milliliters, it's 12.52. 12.52. So these are the pHs that were calculated doing the exact same method of the 30 milliliters. And so let's plot that on our graph. So we have 12.22. So at, what was that, 35? So we have 35, 12.22. So that's about here. And then we have 12.36 at 40 milliliters. So that would be here. 12.36. That is correct. So 12.36 here. So it's going to be about here, 12.36. And then at 50, which is here, that's going to be 12.52. So 12.52 is going to be about here. So this should be like a little bit lower. So 12.52 is going to be a little bit like maybe there. And so this is what the graph looks like. And so if we connect the dots, you'll see that the graph looks something like this. So here we go. Like so. So this is what the graph looks like when you titrate a weak acid with a strong base. And so some features I want to point out that you'll notice. So first, you'll notice that the first point that you calculate the pH, the initial point is a weak acid problem. So the way you calculate the pH there is you just treat it like a weak acid problem. You figure out the equilibrium equation, and then you set up your ice table, and you go through the process of figuring out what X is, and then get the pH from there. So that's the first point. In between the initial point and the equilibrium point, so all of these points, you've got a buffer problem. So this is a buffer problem here in this area. And so again, the way you're going to treat that is a two-step problem. So you're going to do the stoichiometry first, figure out how many moles you have of each of your species, your base, your acid and the conjugate base. Once you figure out that, then you got to figure out what the concentrations are, because remember, you're adding volume to the 25 milliliters there. So you got to recalculate your volume, figure out what the new concentrations are, and then plug that into your Henderson-Hasselbalch equation to do the equilibrium part, right? So you got the stoichiometry part, and then after the stoichiometry part, where you do your after you do your before adding the base, after adding the base, and after adding the base. So you got that table. Figure out the moles that are left over, figure out the concentration from the new volumes, and then plug that into your Henderson-Hasselbalch equation. So that's what you're going to be doing here in between uh, the initial concentration before you add any base, and the equilibrium point where you've neutralized all of your acid. So it's a buffer problem. Again, I want to point out that the uh, the half the half point of your equivalence point, the half equivalence point, where you're halfway, you've added half the volume you need to get to the equivalence point. So since the volume here to get to the equivalence point, the volume of NaOH I need to add is 25, then 12.5 is half of that. And we know that at the half equivalence point, the pH is equal to pKa. Also, in this area here, after the equivalence point, this is now a strong base problem. So when we get to the equivalence point, before I get to here, at the equivalence point, it's a weak base problem, because all you have left here, all of your weak acid is neutralized. So what's left over is just the conjugate base of the weak acid. And so this is a weak base problem. So you treat this like a equilibrium problem, but with the base. And so you're going to use that to find the OH concentration, and then use that OH concentration to find the H plus concentration, and then use that to find the pH, just like I showed before. And then after the equivalence point, this is a strong base problem. So here's where you're going to have an excess amount of OH minus. And at this point, we can ignore the weak base, because the OH minus is going to overwhelm the weak base. So we can ignore that and just focus on what's the leftover OH minus, what's the excess OH minus, and then use that to find the pH. And so those are the important parts of the graph. And just to make mention of the fact that we could, instead of a weak acid being titrated with a strong base, we could do a weak base and have that titrated with a strong acid. And the only difference there is that this would be flipped, so you'd have a mirror image. So since we would be starting with a weak base, you'd have a high pH to start with. So your initial pH would be high. So you'd have a pH up here, and then as you add the acid, the strong acid, to neutralize the base, the pH would go down. So as more and more acid is added, the pH would go down. And then what would happen is, when you get to the equivalence point, just as the equivalence point when you're titrating a weak acid with a strong base is basic, because you've got leftover conjugate base at that point. For when you're titrating a weak base with a strong acid, once you've eliminated all of the weak base, the only thing you have left over is the conjugate acid. And so that conjugate acid is going to make the pH go lower than 7. So you're going to have an acidic pH at the equivalence point if you are titrating a weak base with a strong acid. So at the equivalence point, your pH, so if this is our equivalence point, our pH might be down here. So we're going to be around 6, or in this area here. So you're going to have a low pH below 7 if you're titrating a weak base with a strong acid. And so when you go beyond that point, now it's just a strong acid problem because now you have excess H plus ions from the strong acid, and the excess H plus is going to dominate and overcome and suppress the weak acid. So you can ignore the weak acid at that point. So basically, this S curve here for the weak acid being titrated with a strong base is going to be flipped. And so that's the main difference. So I hope this is helpful. If you enjoyed my videos, please hit that like button right there, and also subscribe to my channel. Hit that subscription bell up there, so that way you can be notified by other videos I put out. Put a comment down in the comment section. Let me know what you think, and if you have any questions or comments. Thanks for joining me. Have a great day.